everyone. Myself Sachineka, Academic Coordinator, Department of Computer Science, Artificial Intelligence and Data Science. Let us discuss about the analysis and design in the software engineering. Analysis and design form the foundational pillars of virtually every successful project, whether it be in the realms or software development, engineering, architecture, or any other discipline requiring the structured problem solving. It serves as the initial stage where the problem space is dissected and synthesized into manageable components. On the other hand, design is a creative process of conceptualizing solutions that address the identified needs and challenges. Together, analysis and design establish a roadmap that guides the development process, ensuring the resources are effectively utilized and that end product meets the exceeds expectations. Architectural design and software engineering. Architectural design in software engineering is a high-level design expressed as a block diagram defining the structure of the software. It determines the structure and features of the components, data flow patterns, and how these components communicate with each other to share data. Types of architectural design. The first one is monolithic architecture. So these are all the key aspects of the monolithic architecture. Monolithic architecture, the operating system is designed in a way that all operating system services, including memory management, process scheduling, device drivers, and file system, are providing a single large binary. So single tier architecture. In monolithic architecture, the entire application is designed and deployed in a single unit. This means that all components, modules, functionalities are tightly coupled and run within the same processor or server. Simplicity. Monolithic architecture tend to be simpler in design and implementation compared to distributed architecture. Developers only need to understand and work within the boundaries of single code base, making it easier to develop, debug, and test applications. Shared memory or resources. Since all components of applications run within the same process, they have direct access to shared memory and resources. This can lead to efficient communication and data sharing between the different parts of the system without overhead of network communication. Ease of deployment. Deploying a monolithic application typically involves the packaging the entire code-based dependencies into a single executable deployment articraft. The last one is limited scalability and flexibility. Monolithic architecture can struggle with scalability as scaling the entire application often requires scaling the entire monolith, which can be inefficient and costly. This lack of flexibility can hinder agility and innovation, especially a rapidly evolving environment. Next one is microservice architecture. These are all the important aspects of the microservice architecture. Service decomposition. Microservice architecture advocates breaking down complex applications into smaller, loosely coupled services, each responsible for specific business functions and capability. Autonomous services. Each microservice operates as an autonomous unit with its own database and business logic. This autonomy enables teams to choose the most suitable technology stack, programming language, and data storage solution for each service. Distributed communication. Microservices communicate with each other through the lightweight protocols such as HTTP or message queues. The distributed communication enables services to deploy independently across different environments and scales more easily than monolithic applications. Scalability and elasticity. A microservice architecture supports horizontal scaling, allowing individual services to scale independently based on the demand. Additionally, cloud-native features such as auto-scaling and container platforms like Kubernetes facilitates the elastic scaling of microservice-based applications. The last one is continuous delivery and DevOps. Microservice architecture aligns well with continuous integration and continuous delivery practices, enabling teams to deliver software updates rapidly and frequently. Service-oriented architecture. These are all the key aspects of service-oriented architecture. Modularity and reusability. SOA Service-oriented architecture encourages breaking down complex systems into modular services, each responsible for specific functions and capabilities. Service abstraction and encapsulation. Service in service-oriented architecture are encapsulated units of functionality that abstract underlying implementations detail from the customers. Interoperability and standard-based communication. It emphasizes the use of standard communication protocols and data formats to enable interoperability between the heterogeneous system and technologies. Service lifecycle management advocates for a systematic management of service through lifecycle from design and development to deployment and retirement. Service governance and policies. It encompasses the establishment of the policies, process and controls govern the creation, consumption and management of services within an organization. The next one is event-driven architecture. These are all the key aspects. Asynchronous communication. The communication between the components is an asynchronous, meaning that components produces and consume events independently of each other. Event-driven messaging. Event are central mechanism for communication. Events represent meaningful occurrences within a system, such as changes in state, user interaction, or system errors. Loose coupling. It promotes loose coupling between the components by decoupling the producers and consumers of events. This loose coupling enables components to be developed, deployed and scaled independently. Scalability and flexibility. Event-driven architecture supports the scalability and flexibility by allowing the components to react dynamically to change the system. Event processing and stream processing involves processing events in real-time or non-real-time, derived insights, triggers, actions and update system state. Event processing involves analyzing, filtering and aggregating events to external meaningful information or detect process. Layered architecture. These are all the key aspects of layered architecture. Separation of concerns. Layered architecture promotes the separation of concerns by dividing the system into logical layers, with each layer focusing on specific aspects of functionality. Abstraction and encapsulation. Each layer in layered architecture encapsulates its functionality behind a well-defined interface, hiding implementation detail from higher layers. Hierarchical structure. Layered architecture typically follows the hierarchical structure with layers arranged in top-down fashion, from presentation at the top, data at bottom. Scalability and extensibility. Layered architecture supports the scalability and extensibility by allowing individual layers to evolve independently. Similarly, layers can be scaled horizontally or vertically to handle increased workload and accommodate changes in the requirements. Finally, we have the standardization and reusability. Layered architecture encourages the standardization and reusability of components within each layer. Common functionalities such as authentication, logging and error handling can be implemented as reusable modules or services shared across multiple layers or applications.